Hello everyone. What I want to do now is go over how to prove that the Hilbert transform is weak type 1-1, at least for Schwartz functions. And I think for a change, I'm going to try to do this as a real-time lecture, see how this goes. Okay, so we first need the following lemma. Okay. And yeah, so the lemma is as follows that we need. So let's say we have an L2 function f. And let's say f is 0 almost everywhere away from a compact set I. Okay, then I claim that the Hilbert transform is given by this integral. Basically, it's the same formula that we proved is true when f is a Schwartz function. Okay? And this is going to be for homework. I'll give hints, but the basic idea is that this formula holds that I'm circling for Schwartz functions. And you use the fact that H is an isometry, or really just need bounded on L2, and then do a little bit of a clever approximation argument. Okay, and this is for so this is actually for almost every x away from I, okay? So if f is 0 on R take away I, of course, this really is going to be, this is going to be on I. So in particular, this integral here, there's really no ambiguity regarding this integral. X is not going to be equal to y, right? And in particular for a fixed x, since R take away I is open, x is going to have x is going to be a fixed distance away from I, so that the bottom here is a fixed amount away from 0. Okay, and I is compact, so there's absolutely no ambiguity in defining this integral. You can smash in absolute values, throw away the denominator, and use Cauchy-Schwarz inequality. So there's no ambiguity in defining this integral. Okay, because again, x is away from I. Okay, so we're going to use this to prove the following theorem. It's actually a little stronger than saying H, the Hilbert transform, is weak type for Schwartz functions. Okay, so all we really need is f not necessarily a Schwartz function, but L1 intersects L2. So if f is an L1 intersect L2, then the measure of the set here, x where h f of x is greater than lambda, is less than or equal to some c times the L1 norm of f over lambda for any positive lambda, where c is independent of f. So let me just move this over here a bit. Okay. Right. Right. So this doesn't prove that the Hilbert transform is weak type on L1. And in particular, we don't know what the Hilbert transform is on L1. Or rather, it's just not defined on L1. Whereas a Hilbert transform is an isometry on L2. So certainly as a function, HF most certainly it makes sense. It's a measurable function. It's an L2 function. Right, so, okay. And let's prove this. So the idea is going to be that we need F as an L1 to do the Calderon-Zygmunt decomposition. Okay. And I should say, breaking F up into real and imaginary parts, breaking up both of the real and imaginary parts into a difference of non-negative functions, standard stuff. We can assume that F is non-negative, just like you did hundreds, probably, well, maybe not hundreds, but dozens of times in 510A. Right? Again, you break F up into its real and imaginary parts, and then both the real and imaginary parts, you break it up into the positive and negative parts. So to assume F is non-negative, so it's an L1 function. All right, so let's say F equals G plus B, which is the Calderon-Zygmunt decomposition. At height lambda. Okay, so right, we pick lambda positive. We're going to look at this set right here for this fixed positive lambda. Let F equal G plus B. So implicitly, as kind of we mentioned, this is really, depends on lambda, but as often as most people do, we don't write the lambda dependence. Just kind of cumbersome. Okay, so as we've done before, not going to really explain this all that much. So the measure of the set that we need is going to be less than or equal to, rather, we want this set here. So it's less than or equal to the measure X such that H applied to G, this good function, is bigger than lambda. And G is an L2. We'll actually very easily prove that in a moment. So H is well defined on L2. And we'll see that B also is an L2. We'll do that in a little bit. So everything here is well defined, nice and measured. Everything's a nice and measurable function. In particular, HG and HB are perfectly nice measurable functions. H is well defined on them. Okay, so this is our task here to get estimates. Sorry, it should be lambda over 2, and it should be lambda over 2. Right, so we need to get estimates on both of these. All right, so we're first going to do this one here. So let's say this is 1 plus 2. Yeah, this is going to be pretty easy. In some sense, the hard work is already done with the Calderon-Zygmunt decomposition. So at this point, maybe it's a good idea to actually pause this and to go back and look at all of the properties for the Calderon-Zygmunt decomposition that we've proven, or rather proved. Actually didn't realize it matters, but you really shouldn't say proven, it's proved. But anyway. Okay, so 1, well, I'll just remind you what 1 is. Taking the measure of the set here. And all we're going to do is take the L2 version of Chebyshev's inequality. So this is less than or equal to this number, well, 1 over this number squared, 2 over lambda squared times the L2 norm squared of HG. Well, this is an isometry, so we really don't even need equals. We just need that H is bounded on L2. And that's important because, well, we'll talk about operators that behave like the Hilbert transform. All right, so, well, remember that, put this in red. So remember that this is less than or equal to 2 lambda. So we get rid of one of the g's. This is obviously like, well, g times g. G is, non-negative. Or, sorry, not necessarily non-negative, but g is real valued. Well, anyway, whatever, doesn't matter. Real valued or not, we can pull out an L infinity norm here. So it's less than or equal to well, the L infinity norm of g times modulus g. And that's 2 lambda. So this is going to be 8. Well, I'll just leave it like this. 2 lambda times this integral here. Okay. And remember, another property that we mentioned is that the L1 norm of G actually is equal to L1 norm of F. All right, so we're basically done for this estimate here. This is going to be 8 over lambda times the L1 norm of F. Okay. So one thing that's really nice about this proof actually is that we're going to get a very explicit constant for C here. I mean, I think it's going to be like 16, maybe 8 or 16, because of the precision with the Calderon-Zygmunt decomposition. Right? Okay. So yeah, that takes care of 1. And again, that's because of the nature of the good function. Often when you do arguments using the Calderon-Zygmunt decomposition, this is just easy to handle. Not that this one is particularly hard, but you just have to handle it with a little bit more care. So let's do 2. Okay. Okay, so first of all, I claim that B is an L2, so everything is fine. And I actually claim that B equals the sum of the BJs, where the sum converges in L2. Okay, so remember what even the definition of B was. Remember, this was very explicit. This was this following sum. F of x minus this average here over the ij's. And remember, the ij's are the Calderon-Zygmunt intervals of height lambda. Right. Right, and remember this here is just shorthand for 1 over the length by j times the integral of f over ij. Okay, and remember that these intervals are disjoint. The ij's are disjoint intervals. Let me just, do this in black. Okay, so because the intervals are disjoint, normally you can't do this, but because the intervals are disjoint, we could take the L2 norm squared, just take this squared, integrate, and we just are basically integrating this whole inside squared, sum up, integrate over ij. Okay, so f of x And again, this is simply because the ij's are disjoint. Basically, it's L2 orthogonality. Right, so, right. Okay, so now you can actually square. So actually, you don't really need absolute values. It's just squared here. F is not negative, so this whole thing is real valued. Okay, so right. So this is certainly going to be well, if you square this, actually, if you square this whole thing, this is going to certainly be less than or equal to, I could just use Cauchy-Schwarz, this sum here. So it's going to be f of x squared so make a big bracket here. Plus the, oh, sorry. Get rid of this. Plus the length of ij. Times the average. And sorry, there should be a 2 here. Times this average here. Okay. And again, you can just really just square this and see this. You really don't even need Cauchy-Schwarz. But I mean, you could use Cauchy-Schwarz to both of these actually to get this. Okay. Right. So. Right. So now let's use Cauchy-Schwarz again to this function right here with respect to these intervals ij. Okay. And these, remember, the ij's are finite intervals, so no issue using Cauchy-Schwarz here. So if you do Cauchy-Schwarz, this is going to be less than or equal to 4 times this sum here. Okay, and this is going to be less than or equal to, remember these intervals are disjoint, so it's less than or equal to the L2 norm of f. And this is, largely, well, we assume f is an L2. F is an L1 intersect L2. So we're assuming that this is finite. Okay. So that implies that B is an L2, and, well, really this proof implies that B, well, maybe I'll write it like this. B is going to be equal to the sum of the BJ's in L2, okay? Yeah, I mean, that's a very, that's very easy. Basically, just subtract off, and then you'll get a sum like this, where you're eliminating finite number of the j's. But because this obviously the sum converges, you're going to get that you have convergence in L2, because again, f is an L2. So it's very easy to show this. We basically proved it. Right, so what does this mean? Well, it means you can pick a subsequence of the j's where point-wise almost everywhere, well, sorry, before I do that, so that means in L2 HB, because H is an isometry in L2, and H is linear. This is an L2, and so finally this implies really taking a a subsequence of the j's, or rather, you know, it's forming the finite. So sorry, you're going to form the partial sums corresponding to the sum here. And for subsequence of the partial sums, we get almost everywhere convergence. So basically what this means is that, so for almost every x, we're going to get the following estimate. And again, this is a consequence of the L2 convergence of HBJ, the sum, to HB. Okay, so the key is going to be now to estimate this sum here. And we're going to do that by using the very explicit nature of the BJs. Remember that this whole thing here, we'll do it in blue, this whole thing here, remember, is BJ. So we have a very explicit, well, yeah, we have this very explicitly, but we actually don't need the explicit nature of the BJs. I'll show you what exactly we need of the BJs. Right. All right, so let's estimate this. All right, so what do? We do a nice little trick. It's extremely elementary and it's very straightforward, but let's say omega is this union here. It's a disjoint union. Okay, and let's say omega star is the same union, but we fatten it up a little bit in the sense that we're taking the union of 2ij. Remember what 2ij means. It's the same thing as ij in the sense that it has the same center as ij. Remember, ij is an interval, except 2ij is twice the side length. Okay, so if you think of ij as basically a neighborhood, you just increase the radius of that neighborhood by 2. Okay. Okay, so, right. So remember that, well, let's get what this measure here is. Okay. I'll explain why in a moment we want this. There's really no trick here. Use countable subadditivity. Okay. Well, 2ij has twice the length that ij has. So this is less than, or rather, it's not less than, it's equal to and remember the measure of ij is its length. And remember, one of the key properties of these Calderon-Zygmund intervals is that this is, you know, the length of these ij's add up to at most, or they add up to, yeah, at most the L1 norm of f over lambda. Well, that's lambda here. Maybe erase a little bit of this. Okay, so let's put this to good use. Let's see how to do that. Okay, so yeah, the little trick here all right, so we need to we want to look at this. We want to estimate this measure here. Okay. Okay, so basically x is either in omega star or it's not an omega star. It's really that simple. That's basically the trick, and it's not a very subtle trick. Okay. Well, so here, I mean, we're actually being pretty generous. Here, if it's in omega star and this whole thing is true, we don't even care. It's still an omega star. Okay. If it's not an omega star and this is all true, well, we need kind of the whole package. So it's either in omega star or it's not an omega star. And here we do care that if it's in this set right here, then, well, h v of x is bigger than lambda over 2. Okay? And the idea is that we don't just want to look at x away from these Calderon-Zygmund intervals. We want to look at x really quantitatively away from all these Calderon-Zygmund intervals. We want it to be a full length away from these Calderon-Zygmund intervals. And I'll draw pictures in a moment to illustrate exactly what I mean by that. Okay, so what does this mean? This means 2, and remember what 2 is. 2 is this here is less than or equal to the measure of omega star. Well, actually, yeah, it's less than or equal to this measure here, plus a measure of this right here. And I'll write it like this, because I'm going to use Chebyshev's inequality in a second. Okay, so while I write this, we know we have a good estimate for this. We just figured that out. It's less than 2 times the L1 norm of f over lambda. That's exactly what we want. Okay. So I should emphasize that this Calderon-Zygmund decomposition was ingeniously devised by Calixto Calderon and Antoni Zygmund precisely for estimates that we need for the Hilbert transform and for operators behaving like the Hilbert transform. Okay. Okay, and let's call this, well, sorry, let's not call this anything. So now I'm at a point where I can just use, Chebyshev's inequality. A little brain fart there. Okay, so I'm going to integrate over this set here. Sorry, I need the 2 over lambda. All right. And, right, let's call this 2b. All right. So to finish up the proof, I need to prove that 2b is less than or equal to a constant over lambda times the L1 norm of f. And I think this constant is going to be 4 or 8, but I think it's going to be 8 anyway. Right, so really all I need to do is I need to prove, well, I got the lambda here, so I really just need to prove that this integral here is less than or equal to the L1 norm, or rather, sorry, a constant times the L1 norm of f. That's what I need to prove, and I will be done. Okay. Right. And so I want to mention something. Everything's been pretty abstract if you think about it. So we haven't used the fundamental nature of the Hilbert transform yet. All we've used is that H is really, it's an isometry on L2. We don't even need that, as I mentioned. We just need H is bounded on L2. We haven't used, so everything's been pretty abstract. And it's now here that we have to use this lemma. We have to use the real fundamental nature of the Hilbert transform. Okay. Yeah, we can no longer do things abstractly. Okay. So, and that's why I like this proof because it is a combination of abstract arguing and very concrete estimates, as we'll see in a moment. All right, so let's do this. Okay, so first of all, right. So let me call this star here, or maybe star star. Yeah, because I already have a star here. That matters. But anyway, I'll call this star star. That's what we have to estimate. Okay, so this is less than or equal to, well, we already mentioned that point-wise almost everywhere, h of b of x in absolute value is less than or equal to the sum of h, b, j of x. So, right, so this is going to be less than or equal to this integral here, h, b, j of x dx. Okay, well, so we obviously have, put this in red here, that ij is a subset of, or rather, sorry, squeeze this little 2 in. Let me just, okay, so 2ij is a subset of omega star. So, right, so if we take complements, the complement of omega star is a subset of the complement of 2ij. Okay, so this is certainly less than or equal to this sum here. And it might seem like we're throwing out a lot. We're basically, you know, or in some sense, we're adding in, rather, the rest of the ij's. They really just don't matter. What really matters is the ij corresponding to this j here, this j here. That's what really matters. And sorry, it's not just ij, it's 2ij. The fact that x is, you know, a quantitative distance away from ij, and that distance is the length of ij, really matters. And again, I'll draw a picture in a moment because it certainly, in this case, a picture is worth maybe not 1,000 words, but a picture really helps. I mean, you probably should be able to draw the picture yourself, but anyway. All right, so let's get down to some nitty-gritty estimating. In particular, all I want to do is estimate this integrand for fixed x. Okay. Okay, so first of all, bj is supported on ij. So bj equals 0 away from, certainly away from 2 times the closure of ij. Whoops. All right, and this is identical. So maybe I'll just make clear that bj is identically 0. Yeah, maybe get rid of the b of x. This over here. Right. So Bj is identically 0 on this set here. Okay, and so what's the point here? The point is, so let's go back to this lemma here. Right, so we have an L2 function. Each Bj is L2. Actually, you sum up the L2 norm squared of Bj's, and you get something finite, the L2 norm of f squared, or it's less than or equal to the L2 norm of f squared. So certainly each Bj is an L2. And Bj is 0 away from r takeaway to the closure of I2, or sorry, the closure of 2ij. So sorry, I'm just using this lemma with respect to the L2 function and the interval, the closed interval that I have right here. This is a compact set. 2ij closure is a compact set. Ij closure is just a closed interval. Okay. So, right. And obviously ij is a subset of 2ij closure, so no issue here. Okay, so the lemma says that hbj of x. Okay, so yeah, so in the next video I'll talk about what's called Calderon-Zygmund operators, which are operators that behave like the behave like the Hilbert transform, and in particular will really isolate the precise features of the Hilbert transform that we really need, and basically throw away all the extraneous information that we don't need. And I'll mention that we have LP boundedness of these operators, and Calderon-Zygmund operators are used in a lot of different areas, particularly in PDE theory, elliptic PDE theory, but probably in other, well, I know in other areas. I know Professor Buchanu needs Calderon-Zygmund operators in some of his work, but particularly they're very germane to elliptic PDE. But anyway. All right, so yeah, back to the scheduled programming. So that lemma that I started off with tells me that this is true. Now, I do not want to smash in absolute values. That would be a disaster, and that just doesn't get me anywhere. Okay? If you smash in absolute values, you can estimate this, and you will see you get something infinite. That really doesn't help. We need that this integral here is less than or equal to the L1 norm of f times a constant. That's our goal. So what I'm going to do is instead use the property, the very important property of Bj that, and this is just part of the Calderon-Zygmund decomposition. I've mentioned this, that this integral here is 0. So why does that help? That basically allows us to basically add 0 in a very clever way. Okay? And how am I going to do that? Well, I'm going to, well, sorry, not add 0, subtract 0, basically, same thing. Okay, so this is going to be x minus Cj. And what is Cj? Cj is going to be the center of ij. Okay? And so there's no y here. So with respect to y integration, it's just a constant. So yeah, you get this equality here because of this fact, this feature here. Okay, so yes, so the time has come to draw the picture. The walrus said. So let's do it. All right, so what's going on here? Right. And it really is not a subtle picture at all. And I also want to mention, I've said this many times, but you can do everything here in higher dimensions, which is particularly what's germane to applications to PDE theory. And if anyone is interested in PDE, I should mention I'm very interested in elliptic PDEs, particularly systems of elliptic PDEs. This stuff is definitely very germane to that and to my work. But anyway, so if I was doing things in higher dimensions, I would draw a picture of squares, which, you know, pictorially represents higher dimensional cubes. But anyway, so here's a picture. We have Cj is the center of my Calderon-Zygmund interval ij, which is, I'm going to draw like this. Remember, it's a dyadic interval. So it's a half open, half closed interval. Okay. And remember what 2ij is. 2ij is the same interval, but twice the length. So basically, if this is kind of like my radius here, I'm just going to go to the left this amount, and I'm going to go to the right this amount. Maybe it's not drawn perfectly, but whatever, doesn't matter. So I don't think I need another color. So this here is 2ij. Needs this, but this length here, I'll use arrows, I guess. Well, this is the length of ij, or rather, sorry. This whole thing is the length of ij. Okay, and so, right, what are we dealing with? We're dealing with x away from 2ij. Okay. So let's just write an x really anywhere away from 2ij. Okay. So I'm not going to need it just yet, but there's no harm in putting it in. So y is an ij. Okay, and you should be able to see, I don't care where it is. Whatever. I mean, I'll just do it right here. Here's y. So you can see pictorially that the you know, basically the distance between x and y can't be more than 1/2 the length of ij. Because you got this, basically the distance, I mean, yeah, I mean, you can pick x here, here, you can say y is here or here, you'll get the same pictorial conclusion that, you know, this is, you know, this kind of green is, it's like x can't get any closer than the green to y. I mean, you know, you have x here, y here, it's like, nope, stop. X can't be really close to y. It's almost like, I don't want to make a joke about COVID, but it's almost like there's a 6-foot socially distancing between x and y that we've imposed, which is, you know, not 6 feet, but anyway, I guess the length of ij could be 6. Anyway, yeah, so, right. All right, I guess I'll keep the green here to emphasize this. And so this is, I mean, it's not going to be surprising that this is extremely useful in estimating things here, knowing that x minus y is quantitatively large in absolute value. And x minus y could be positive or negative, depending on where x and y are. Okay. Anyway, so let's get back to estimating. Okay, so first of all, let's do something absolutely trivial. So let's add this up. So this is going to be 1 over, what did I say, x minus cj. Is that right? Yeah. All right, so what do we do? Just get a common denominator of, yeah, so this is going to be x, oops, sorry about that. Okay, so, right, we get this common denominator of, right, so it's going to be x minus cj, x minus y, 1 second, whoops, sorry about that. What I'm doing makes no sense here. Sorry about that. Okay, so we have a common denominator of x minus y, x minus cj. Okay, so what do we have here? Oh, well, multiply and divide by x minus cj. Multiply and divide by x minus y. And let's not do a pre-calc mistake. Let's do the brackets correctly. Maybe just move this over a bit so I have room. And you'll notice something is that the x's cancel, which is absolutely crucial. So it's y minus cj over x minus y, x minus cj. Okay, so, right, so let's finish up estimating the Hilbert transform of Bj at x. So at this point, I am now smashing in absolute values, okay? But using this, what we actually found this to be. And it's crucial. We're not going to use smash and absolute values and use triangle inequality. That would basically get us nowhere. Okay, so this is going to be less than or equal to this integral here, ij, absolute value of bj, cj minus y, y minus cj, cj minus y, doesn't matter, over x minus y, x minus cj. So I want to do, I'm going to use Fubini's theorem in a little bit, but what I would like to do, if I can, is get rid of this absolute value of x minus y, which would make, you know, if we can get rid of, if we can get rid of an x here, then I can actually very easily do the x integration and basically compute the x integration, which we'll do. So what do we have to do? Well, so I claim that, I claim that the absolute value of x minus y is bigger or equal to 1/2 times the absolute value of x minus cj. And if I have that, then this is going to be, well, sorry, before I do that, well, let's do that. Let's actually do that. And I'll show you why in a second. So it's going to be, well, I said there's a 2, so, or 1/2, so let's put a 2 here. Cj minus y over, so it's going to be x, well, it's really this squared here. Okay, and why is this true? Well, let's just see why. Okay, so x minus cj And I'll go back to the picture in a moment. Let's just use triangle inequality here. Okay, so I want a lower bound for absolute value of x minus y, so this is good. So x minus y, y minus cj. Okay, well, we know absolute value of y minus cj is less than or equal to the length of I over 2, or length of ij over 2. And that's just because ij is, I mean, this is ij right here. Okay, ij is basically this neighborhood of radius, the length of ij over 2. Y is in it, so yj minus cj, cj is the center of this interval. An absolute value, yj minus cj, and absolute value is less than or equal to length of ij over 2. Nothing subtle there. Okay. On the other hand, so I'll put this in, I guess, red. So, right, so the absolute value of x minus y is bigger or equal to the length of ij. I basically said this already. I'll go back to the picture in a second. So first, let's yeah, so let's use this first. So let's not, I don't want to get rid of, well, that would give me the wrong direction. So you can't even replace this with L of ij over 2 if you wanted to. So let's get rid of this. So it's just going to be 2 absolute value of x minus y. And so, yeah, that means 1 over absolute value of x minus y is, or rather, no, that's right. Sorry. That's exactly what I wanted. This is going to be less than or equal to, divide both sides by 1/2, flip it, 2 over absolute value of x minus cj. And that's exactly what I did here to here. I basically got rid of the x minus y and instead made it 2 over x minus cj in absolute value. So you got 2x minus cj's, hence squared. Okay, so why is this true? Well, so here's why. And basically, yeah, like I said, I already said this. The absolute value of x minus y is bigger or equal to this green length. This green length is the length of ij over 2. It's by definition, basically, because x is away from 2ij. And that's why we need to deal with 2ij. Okay? And if you have any doubts, this is very easy to prove if you really want to. Super duper carefully prove it, but by a definition of 2ij, it's fairly obvious. And like I said, obvious from the picture. Okay, so, right. Now, we can actually, blue. So we can actually use this inequality up here to get rid of the cj minus y, and probably should have done that earlier, but it doesn't matter. Okay, so we explained this here. So now let's exactly get rid of this here. So this is less than or equal to 2. Well, rather, 1 second. Right, so it's going to be 4. Yeah, because I have a 2 here, and I get another 2, another 2 here. well, actually, 2's cancel. So y minus cj is less than or equal to 1/2 times, not that these constants matter, but oops, well that. Okay, so this is going to be ij times this integral here times the length of ij. Get rid of this here. Again, the 1/2 cancels this. Over x minus cj squared dy. Okay, and this is really the pointwise estimate that we absolutely need. And if you'll remember, we know something about the sum of the L1 norms of the BJs over IJs. You know, it's less than or equal to the L1 norm of F. Okay. All right, so what do we need to do? We need to estimate this integral here. Well, sorry, we need to really estimate this here. So let me call this whole thing here star, star, star. So let's estimate this whole thing here using the pointwise estimate we just proved. Okay. So we finally, well, we're going to have to do a tiny bit of work to do this here. So this sum here, our takeaway to j. Okay, dump this estimate in here. I'll pull out the Lij x minus cj squared. Okay, and it's going to be this integral here. Move this up a bit. Bj, whoops, ij. I mean, bj is supported on ij, so it doesn't, not incorrect to write this. So b of, no, that doesn't make sense. B of y, sorry about that. Forget I ever wrote x there. Okay, so, right, now I can use Fubini's theorem. Okay, so it's going to be this sum here. So I can actually even break this up into, it's just a product of these two integrals. So we've actually done a pretty damn good job of estimating things. Right? So the hope is, remember, like I said, if everything else was a constant, we'd be done, because the sum of these integrals by the Calderon-Zygmunt decomposition property that we proved is less than or equal to the L1 norm of F. And that's exactly what we need. So that's what we have to do. We have to try and get the x integral to be bounded by a constant, independent of j. And that is not hard at all. Okay, this is literally a calc 2 integral. Okay, so right, so let's just go back to the picture here. All right, so right, so we're integrating away from 2 times ij. All right. So, right. So really this is going to be, let's see, 1 second. Right, so we can really write this as x. Well, yeah, let's be a little. Let's be a little careful here. Right. So, all right. 1 second. Okay. So yeah, we're going to focus on this integral right here. I don't know what to call this. 4 stars, something, whatever. Okay, so yeah, so let's just be a little careful here. Our takeaway to ij is going to be, so it's going to be this interval here minus infinity. Well, let's see what it is based on picture. So it's minus infinity to this point here. This point here is Cj minus the length of ij. And I think this is going to be closed. It does not matter one bit. I think this one's going to be open. So this is going to be Cj plus the length of ij to infinity. Okay, and that is just, that's exactly what this point is here. This point here is Cj plus the length of ij, right? Okay, so this integral here, star, 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 star. I should just rewrite it, but whatever. I'll do this in black. All right, so this is going to be minus infinity to Cj minus L of ij plus Cj plus L of ij. So it really is not a subtle estimate at all. 1 over x minus Cj squared. I'll just put a dx here even. Okay, right, so you literally do this integral. Whoops, don't want to forget the length of ij here. You don't want to forget that little guy there. It's pretty important. Right, dx. So yeah, you do this integral here. Just a little guy or gal, whatever. Yeah, you do this integral here. You are literally going to get, well, because you have 2 integral signs, you get 2. You get another 2, well, actually, yeah, you actually don't get a 2, another 2, but because it's 2 integrals, you get, this is literally equal to 2, well, 1 over the length of ij. Make this in brackets. And this literally is a calc 2 integral times the length of ij. This length of ij is exactly this one right here. All right, so this is going to be equal to, well, just 2. All right, so let's go back here. This whole thing is going to be equal to 2 times the sum here. And again, by the Calderon-Zygmunt decomposition estimate, or that property, this is going to be, well, it's fairly trivially equal to 2 times the L norm estimate of B, which is less than or equal to 4 times the L norm estimate of F. Okay, so let's put everything back together. This is the integral I just estimated, and this whole thing here is exactly what I wanted. This integral here. The measure of this whole thing here is less than or equal to 2 times the L1 norm of F over lambda, plus 2 over lambda, this whole thing here. We just estimate this whole thing here by, actually we just got it to be 8. Is it 8? 4. So we got it to be 4 times the L1 norm of lambda. And I'll basically put all this up for you to, I'll put this up in a PDF for, it'll help everyone follow. I'll make this a little bigger, not that it matters much. This. Anyway. Where am I? So yeah, this is actually less than or equal to, where did the eraser go? Four times the L1 norm of F. Okay, so that makes it 8. This is a 10. So what did we get from previous one? This was 8. So 10, 8. I believe it's going to be actually 18. All right, so the conclusion here is that this set here bigger than lambda is less than or equal to 18 times the L1 norm of F over lambda. When you do this in higher dimensions, you really don't, you get a dimensional bound, something like 2 to the n plus 1 or something, or maybe not, I mean, something like a constant times 2 to the n. But anyway, you still get a pretty nice concrete bound in higher dimensions. Okay, so that finishes the proof. Right, and we'll talk in the next video about how to define the Hilbert transform on L1. And it's basically the same situation we were in with the Hilbert transform. The integral, the definition of the Hilbert, for the Fourier transform. The definition of the Fourier transform for an L2 function is not the integral. It makes no sense necessarily. There's no reason why that integral should make sense. So we have to play games with, pick a sequence Fn in L1 intersect L2 that converges to F in L2, and use that to define a Fourier transform. We're going to do the same thing here. We're going to use the fact that we proved this for F and L1 intersect L2 to extend the Hilbert transform to L1 functions. Right. All right, so hopefully this all made sense. Yeah, like I said, I'll put up a PDF for this to maybe make more sense, or for you to maybe make it a, I mean, it should have been pretty straightforward to follow. but maybe to make it a little, even just that much easier to follow. All right, yeah, hopefully this was informative, useful, helpful, and great. All right, so one more video and we're done. So, all right, take care. Bye-bye. I'm having a hard time ending this like that. All right, bye-bye.